In this video, we're going to look at a variety of direct alkylation reactions. What we're going to do is we're going to use these carbanions that we've been generating adjacent to ketones, and we're going to now be treating them with alkyl halides. The role of the alkyl halide, remember this, is merely a substrate for the SN2 reaction. So everything you already know about the SN2 reaction goes for the alkyl halide in this reaction. It works best with primary, it works best with iodides, benzylics, and allylics tend to be a little bit better than the compounds that don't have the double bonds, and generally you can't do this using halides at sp2 carbon. Okay, all right, so let's look first at the simple direct alkylation of a ketone. And what we see here is two ways to do this. We're going to look at it first like we do the aldol condensation, where we use a base that's not quite strong enough to completely remove the adjacent or the alpha proton, and then we're going to look at using stronger bases where we can completely remove the adjacent or the alpha proton. Okay, all right, so and the first one up here, the base we're using is potassium T-butoxide. Remember, the pK here is about 20. T-butanol, the pK is about 19. Okay, so this equilibrium favors the left side. But once we generate the enolate, or the I'll just draw them as carbanions here. Okay, so once we generate this, it's going to be very reactive to an alkyl halide, like methyl iodide in this case. All right, and we're going to do a nice, good old-fashioned SN2 reaction, and that's going to put a methyl in the alpha position. Okay, sometimes this procedure works, but often it's complicated by the over-alkylation. Okay, so here are some byproducts we could make. We could make a variety of products from putting two methyl groups in there. Another carbanion-based reaction is the aldol condensation, so we might make this aldol product here also as a byproduct. Okay, so this is usually not the preferred way to do a direct alkylation because of these competing processes. Okay, so the reason we have the over-alkylation is because we still have a lot of protons that could be removed in our product. And there really isn't that much difference in the acidity of the compound I've deemed the major product there in the starting material. Okay, a better way to do this is through kinetic enolate generation. Okay, so we're going to treat this now with our old friend LDA. Okay, and this is a very strong base. Remember that diisopropylamine has a pK of about 33. So this reaction is going to go completely to the right, and the arrow going to the left is really negligible here. All right, so we're going to generate this at low temperature, and if you add the methyl iodide rapidly all at once, you'll get predominantly this product here. You have to kind of add it directly, because if there's a time when reaction's like halfway over here, and these two compounds are both present. One of the things that can happen is that these two can swap protons, and you could conceivably get over-alkylation reactions, so you have to be very careful how you add the methyl iodide. Okay, here's a compound here that has two enolate possibilities. Remember, LDA is quite a hindered base, and it typically goes for the less hindered proton, and that would be one of these two, and not that one right there. So this would be the major enolate that we get, and when we treat this with a good SN2 substrate like allyl iodide, we could expect to generate the product that you see right here. We might get some product from this one, but not very much, because this is going to be only a minor product. So this should be by far the major product. Okay, let's look at a more convenient way. One of the problems here with this kinetic enolate formation is it requires a lot of skill. Okay, the person who does this has to very carefully exclude the water from their starting material, their base, well, obviously from the base, and from their solvent. Okay, and you have to do it under conditions where water doesn't come out of the air and quench your reactive compounds like the enolate or the LDA. Okay, and if you're working in a system where it's very cold, like minus 78 degrees, that is a way to sort of trap or bring condensation out of the air, okay? And that's kind of a hazard here. So you have to be very careful how you do it. Usually you use a positive pressure of nitrogen gas to do this, and this requires a little bit of skill. All right, let's look at a way that doesn't require so much skill, and this is called the acetoacetic ester synthesis, okay? So it looks kind of convoluted here. It's quite a few steps. So our starting material is not going to be a ketone, but it's going to be ethyl acetoacetate very often, which is a generic example of a beta keto ester. Okay, because this compound is so acidic, its pK is about 11, it reacts with relatively weak bases like sodium ethoxide and ethanol, and this will make now the anion, and you can alkylate this in a classic SN2 reaction to produce the compound here. Okay? All right. Now, what if you don't want this extra ester here? Well, it's pretty easy to get rid of it using reactions we already had before. So we're going to do an ester hydrolysis. That's going to turn the ester into a carboxylic acid. Okay? This carboxylic acid now has a beta oxo group. And remember, these types of carboxylic acids can undergo thermal decarboxylation. Okay, so these can lose CO2. And if you lose CO2, you get the alkylated ketone. Recognize that this is the same product you could have gotten from alkylating just plain old acetone at low temperature, but this is much easier to do. Okay, even though it's 3 steps, the average person, experienced or a rookie at organic chemistry, will probably get a better yield of product using this 3-step acetoacetic ester route. Another nice thing about this is that after you've added it once, you can actually remove the second proton and add a second alkyl halide. Okay, and after you do the ester hydrolysis and decarboxylation, you get the doubly alkylated analog of acetone. Okay? All right. Let's see. I said it's 3 steps, but if you do an acid-catalyzed ester hydrolysis like this in this blue line here, and you do it at high temperature, that's kind of brutal conditions, but you will be able to get the ester hydrolysis and the decarboxylation done in one step instead of 2. So it goes a little quicker if you do it that way. All right, so let's do a couple problems here. These are acetoacetic ester syntheses of your own. And let's just imagine what our final product is. All right, so let's look at the first one. And again, you should pause the video, do it yourself, and then restart it and look at the answers. All right, step 1. We have 2 alpha hydrogens here. We're going to remove one of them, make an anion, and this is going benzyl bromide is going to be our alkyl halide. Okay, so step 1 should put the benzyl group into our product. All right. Step 2 is the same step. We're just going to use the remaining hydrogen here, and we're going to now do an SN2 reaction with isobutyl tosylate. That's going to put an isobutyl group in our molecule. Okay, there's our isobutyl group right there. Isobutyl group from the tosylate right there in an SN2 reaction. All right, then we're going to, in these two steps here, we're going to hydrolyze the ester. It's going to become a carboxylic acid, and then we're going to lose CO2. And our product is this product right here. Okay? All right, in this next one, it's already partially alkylated at this very acidic position. So we're just going to, in step 1, put in this group here. The propargyl group is what this is called. Okay, and that goes in right there in an SN2 reaction after we make the anion. And here we're doing this one-step decarboxylation ester hydrolysis. The product that we're expecting to get from this is just this, the methylacetylene group on the cyclohexane ring. Okay, excess. I don't know, I have kind of a cuss word there. Sorry, excess. Okay, sorry about that. All right. So we're going to use excess sodium ethoxide here. It has to be greater than 2 moles. Okay, recognize that this is a dihalide. All right, so what's going to happen here is that let's see, 1, 2, 3, 4, 5, and I have 4 there, so okay, excellent. All right, so we're going to make this initially. All right, we're going to, sorry, I haven't left myself all that much room to write here. When we pull off the anion, or pull off the hydrogen to make an anion, sorry, okay, we can do a process known as an intramolecular SN2. But since we've had an excess of base, we can do the double protonation and get both of these to add. The first one is an intermolecular reaction. The second one is an intramolecular reaction forming a 5-membered ring. And this is the product that we would expect to get, a ketone with 2 cyclopentyl groups on it after the ester hydrolysis and decarboxylation steps. Okay, there's an analogous procedure that makes carboxylic acids instead of ketones, and this is called the Malonic ester synthesis. Okay, so this uses diethyl malonate. It's not quite as acidic. Its pK is about 13, but it undergoes a similar series of steps. Okay, all right. Sodium ethoxide pulls off the proton. Alkyl halide does an SN2 to give us the substituted product here. We can hydrolyze the ester, either the 1-step route in blue or this 2-step route, and this gives us the carboxylic acid that's alkylated in the alpha position. Just like with the acetoacetic ester synthesis, we can do 2 SN2 reactions if we just take this acidic hydrogen here and deprotonate it again. Another SN2 reaction would give us this, and this would give us the product. Okay, something I forgot to say before, but I'll just say it here. Notice that the base matches the alcohol group of the ester, and this is because if you don't have this match, you'll get a transesterification reaction as well. So if we use sodium methoxide, we might see some of our COOET groups turn into COOMe groups. That's not really a problem for this chemistry, except if you want to isolate these things halfway and look at their NMR spectra, you would find that they would look kind of messy if they had mixtures of ethyl and methyl groups in them. Okay, all right, so the the malonic ester synthesis produces a substituted carboxylic acid. Hypothetically, we could have gotten the same thing by just taking ethyl acetate here and treating it with LDA in -78, but this way is far easier to do. It doesn't require really ultra dry solvents. They should be as dry as you can possibly get them, and the compounds that we're making here, we don't have to use such ultra strong bases to generate anions. Okay, so this malonic ester synthesis is much easier to do than the direct alkylation. Okay, so the rest of this video is just going to be involved with doing some problems, I believe. Yeah, so here's another problem. We're just going to predict the products of these are malonic ester syntheses, but they're the same general idea as the acetoacetic ester syntheses before. If we look at step 1 here, okay, here are our acidic protons. This is not diethyl malonate. This is called Meldrum's acid, but it's the same general idea. Okay, so our first one is going to put in the allyl group. Okay, our next one is going to do an SN2, and it's going to put in this ether group here, step 2. Okay, we're going to have an allyl group here, and we're going to have this ether group, benzyl methyl ether. Then we're going to do an ester hydrolysis. This is a cyclic ester, but or a lactone, but it'll hydrolyze just like an ester. Okay, we'll just look at step 3 here. Okay, so you get that dicarboxylic acid and then heat it to a high temperature and blow out CO2. And this is what you would end up with right here, shown in blue. All right, so here we're just going to add this alkyne substituent. To a substituted diethyl malonate. Sorry. Okay, we're going to hydrolyze the ester and blow out CO2 in the same step. Okay, so the ester we get isn't going to be a stable compound. Okay, it's going to lose CO2, and the product that we get is the one here. All right, again, I spelled excess wrong. Sorry. Here we have 5 carbons in our substrate, so we're going to actually add 5 more carbons in a ring here, step 1. Okay, I won't go through the details like that in the detail that I did with the acetoacetic ester synthesis, but you're going to make a 6-membered ring when you do this. Okay. Step 2 is going to put carboxylic acids there. And step 3 is going to get rid of a carbon dioxide molecule. And the end product is cyclohexane carboxylic acid. Okay, this is a multi-step synthesis problem. This is a very common type of problem that you usually see on exams. Use the Malonic ester synthesis to perform the following transformation. Okay, the Malonic ester synthesis is central to everything here, but you'll recognize that the product is not a carboxylic acid. So something has happened to the product of the carboxylic acid, or something has happened to the carboxylic acid product to get this, okay? So I've given you a hint here. Only the 2 asterisk carbons are actually going to come from diethyl malonate. Remember that in diethyl malonate, we blow one of them away as carbon dioxide. Okay, so let's look at how this how this synthesis here is accomplished. All right, the final step is going to be, basically, we know that we can produce a primary alcohol from a carboxylic acid by a hydride reduction. So that is the last step of the reaction. And right away, now you see it as a malonic ester synthesis product, right? Okay, so that's a direct malonic ester synthesis product. Okay, so if we look at the carbons that are coming from diethyl malonate, it's only this part of the molecule. So what do we have to do? We have to install a methyl group and we have to install a pentenyl group. Okay, all right, so let's forget that I advanced that. We have to install a methyl group and a pentenyl group. All right, so all we do here in the malonic ester synthesis is we're going to take diethyl malonate. We'll call this step 1, sodium methoxide methyl iodide. Step 2, sodium methoxide pentenyl bromide. Okay, and that gets us this precursor here. And so all we have to do is hydrolyze the ester and decarboxylate, and we got our product, okay? All right, so let's look at a hypothetical situation. Let's say somebody reversed steps 1 and 2. How many points do I take off for that? Well, the answer is none, because there's nothing telling you have to do it this way, okay? If you actually did it yourself, you might find that one way gave you a better yield or a cleaner reaction or something like that, and you did it. You would use that as your method, but as far as like hypothetically planning a synthesis, either of these are equally good. Okay, so we're going to look at some more syntheses. Let's just look at the most common mistake. And this is kind of a fault of the way that we have taught the course. All of your organic synthesis problems, for the most part, had turned simple molecules into more complex molecules. Basically, you don't lose carbons in any of your previous syntheses, right? And this is one where there is a deliberate loss of carbons, okay? We're going to lose that whole group. So a common mistake that people make is they try to find some way to turn this into a methyl group or a pentenyl group, and that's not what you do. Those carbons are lost. So remember that You use those carbons to make your adjacent hydrogens very acidic, and then you get rid of them. Okay, they don't show up in the final product. Okay. All right. So here's a couple of other organic synthesis problems based on the malonic ester and acetoacetic ester synthesis. We're going to go through them one at a time, but the first one involves turning diethyl malonate into that amide, and recognize that carboxylic acids are the product of the malonic ester synthesis. But we know how to turn carboxylic acids into amides. No big deal there. Okay, this one, it's got not only, well, it's not a direct ketone like you see in the acetoacetic ester synthesis, but we see a tertiary alcohol. And we know that when we add Grignard reagents to tertiary alcohols, we'll actually get these types of products. Okay? All right, so let's look at this one. All right, so remember that that ester group is eventually going to be removed through hydrolysis and decarboxylation, and that only the asterisk carbons are coming from that starting material. The groups in blue, they're going to have to be added, and the red group, we're going to have to adjust the group here since the malonic ester synthesis gives us the carboxylic acid. All right, so the groups we have here are a benzyl group and a, I guess, isopentyl group. All right. So our last step is going to involve turning our carboxylic acid product of the malonic ester synthesis into an amide. All right, easy. Make the acid chloride and treat it with an amine. That'll give us the amide. Okay, so now we need to install those alkyl groups. Okay, so we're going to install the benzyl, then install the isopentyl. That gives us product here. And we're going to get rid of that ester group there by hydrolysis and decarboxylation. And remember, if we call this step 1 and step 2, step 1 and 2 could be reversed. A lot of people, here's another mistake some people make. They'll actually reverse steps 2 and 3. Well, it turns out no, because the compound really isn't all that acidic anymore, okay? Or even 2 and 4, okay? We need to have both COOET groups present for these alkylation reactions. Okay, you can't get rid of these COOET groups until you've gotten all of your alkyl groups into the molecule. Okay, all right, so let's look at this one, ethyl acetoacetate. Okay, so it's going to be transformed into this. The blue groups, those carbons are going to have to be added. I should also say that this carbon here, one of these methyl groups, is going to have to be added because we've only got one methyl group in the starting material. We've got 2 of them there. Okay, we're going to form the bonds that I've shown in magenta, and the red carbons, okay, or the asterisk carbons, are going to come from ethyl acetoacetate. Okay, so our last step, since we know that we get a ketone from the acetoacetic ester synthesis, is just to add a Grignard reagent to the ketone. Okay, thus this is now really the molecule we want to make in the acetoacetic ester synthesis. We have two allyl groups. Okay, so we're going to allylate once and allylate twice. It doesn't matter which order you do these because they're the same alkyl group that you're adding. Okay, after doing the alkylation, you'll get this. And then you just do the ester hydrolysis and decarboxylation to get rid of that ester group right there. I think this is the last slide in this video, and I think there will be one more at some point. Yes. Okay. All right. So anyway, that's all for this one.